this ties into the last lecture on superalloys. You'll see a bunch. One is intact, and the other is not only attacked, but deformed. It has an S shape. It has some form of wear, so it's pretty much beat up. One thing that I don't think I mentioned about the superalloys is the composition. Typically it's nickel based with some cobalt, but you also have cobalt based superalloys. It really depends how high of a temperature you need to go to and the corrosion resistance that you need. So this specific component just went to a beat up because we know it suffered creep damage because it formed an S shape on the blade itself. We call these a cluster when you have more than one holding together. It suffered this form of microstructural attack. I don't know the details of it, but we can see cracks that are extending beyond the area that was shattered. So the whole microstructure became brittle, and that's how you had a cracking and a premature failure. So as far as today, we're going to continue going towards these stiffer materials. If you remember the little chart I started the class with, we have essentially from polymers going to aluminum, titanium, we have steel, we have the superalloys. So we're all the way there now in the stiff material, the ceramics. We're going to talk a little bit about metal matrix composites. I have a good example of for wear-resistant design there. And we'll talk a little bit about titanium, but I'll be really brief because Matt is going to do his term presentation on titanium, and he's going to talk more about processing from what I understand. So I'll be very brief with respect to titanium. Ceramics, I couldn't, because we have this series on material selection, I felt we have to cover it, even though it's really not used as much for a structural application. The reason is the low fracture toughness. So you can have some ceramic components for wear application. They use it typically as inserts. But as far as having a solid piece of ceramic that you're going to rely on for toughness, impact, resistance, it's relatively rare. We're mostly going to focus on the advanced ceramics. So traditional ceramics, what we have for any household items for cooking, is interesting maybe to some people, but we're not going to spend a whole lot of time there. So this is pretty much what I want to cover for ceramics. The ceramics, we think of them as brittle, but as you increase the temperature, they will suffer the same types of damage mechanism that we have for metal. So on the plot here, essentially showing a slow crack growth and creep as processes that happen. It's high temperature, so we're looking at about 1200 degrees centigrade, but it's not that different from the superalloys that we were looking at the last lecture. So we can't think of ceramics as being always that brittle material. There are conditions where it will actually deform plastically, permanently, creep, and all of it. It's relatively resistant to corrosion and oxidation, and that's something that is attractive to a number of applications. If we look at the properties, and I know that I've put a lot of information here, but I guess if we just focus for now on the last column, we have the service temperature. So it varies from about a maximum service temperature of about 1,000 degrees centigrade to 1,400. It's relatively high modulus, although here when you start to stabilize the ceramic here, your modulus is going down. It's close to what it is for steel. Has a low thermal expansion coefficient, relatively low density. So if we could increase the fracture toughness of these ceramics, it would be advantageous for high temperature application as opposed to superalloy. You're looking at, maybe 2.5 times less density than the superalloys. And that's why there's been a lot of work trying to improve the fracture toughness of these ceramics. So I have silicon nitride here of different kinds, and you can see that depending on how you process it, you get different properties. Silicon carbide, the zirconia, partially stabilized. We're going to talk about it in a little bit more detail because it's one of those interesting ceramics where you can increase the fracture toughness through this deformation-induced transformation, and we'll go through the details of that. So I complained a little bit about the low fracture toughness. We're looking at for real ceramics only 3 to 5 megapascal square root meter. It's very low. I mentioned yesterday we had essentially a seminar yesterday as opposed to a lecture that people designing the engines, turbine engines, will not want to rely on a material with a fracture toughness less than about 15 megapascal square root meter. So as far as a pure ceramic, you're just really far from being willing to rely on it, and that's why they have these ceramic-based composites to increase the fracture toughness. So here we're looking at these stabilized systems, and we have the magnesium partially stabilized zirconia, where we have this fracture toughness between 11 and 14 megapascal square root meter. Now, these are not design allowable. These are, you do the experiment and you get this range of data. So if we had to do a design, and you tell me when you go to the lab you get from 11 to 14, well, probably say, well, we're going to use 8 or 7, something lower, because we have variability, and that's a problem when it comes to design. You can still see an improvement. We're looking at about 2 or 3 times more fracture toughness than a pure ceramic here. And what happens, I believe, did I include? Yeah. What happens with the zirconia in particular, and this is not something you have to worry too much about, this whole phase diagram, but you can see essentially in this line, if you follow this line, you're at high temperature and you're cooling down with pure zirconia, and you're going through a transformation from tetragonal to monoclinic. Both structures are not the most deformable microstructure. If you remember when we were talking about aluminum, it was definitely cubic. It was actually face-centered cubic. So these crystal structures are not really deformable to begin with. What happens though when you go from that tetragonal, which is the high temperature phase, to the monoclinic, is you have a growth in volume. So the idea here is to process the ceramic to keep the tetragonal phase down to the ambient temperature. And when you deform, you essentially, if we remember a little bit about our fracture concepts, we had this notch specimen, and I can put a crack in it right here, and we have plasticity. Even in these ceramics, we have a little bit of plasticity. You have tension anyway, triaxiality tension in this area that will induce that transformation from tetragonal to monoclinic in service. Now, the transformation is only going to happen if you're below that 1200 degrees centigrade. So there's always going to be a limit for applying these concepts here. But if you do manage to have it essentially in your tension zone, now you're growing the material and you will reduce the tension, possibly even go into compression, depending on how much of that transformation you are activating. And that's how you increase your fracture toughness. When we talked about it for steel, we had the trip steel, so transformation induced plasticities. It's very similar here, but for a ceramic. And the way you can achieve it is by getting a metastable, so a phase that is not the phase from this phase diagram here. So you keep the high temperature phase. When you have the stress, it just expands. It's possible to do this even with the coatings. Last lecture we talked about thermal sprayed coatings. So you can project on a piece of metal, say a super alloy or piece of steel, a ceramic alloy. It will be this partially stabilized zirconium, and it will go through that transformation and essentially have more toughness than the ceramic alone. That was really brief. Any question on ceramics? So I wanted to cover it because I want you to have as much exposure to the different alloys. I feel like if we just neglect it, you're gonna think it's unnecessary. But there are applications for pure ceramics. Typically as inserts, typically you're gonna want to increase the fracture toughness. And then we say it's good for wear resistance, but the brittleness is always a limiting factor. If you have wear, it means you have contact, and you may have thermal stresses, so you need cracking resistance, and that's why a lot of times we go to these metal matrix composites, which is the next section that we're going to talk about, as opposed to a pure ceramic. So anything on ceramics, anything that, because I've been, again, very brief. I talked a little bit about the toughness, the composition. We haven't really talked about how it's made, actually. So typically, you're going to start with a powder, and you can use a binder to essentially form the shape. And then you're going to raise the temperature to the point where you start to diffuse and sinter, we call. So you join together the particles that are adjacent to each other. And that's essentially how you get a solid piece that has toughness. Now you can think of this as a process with a lot of variables. Depending on how fine your particles are to begin with, you're going to get and whether they're spherical or whether they are very granular is going to affect how high of a temperature for sintering you need to be at. There's another key term that's called vitrification. The idea with vitrification is you will partially melt one of the components that you assemble in your ceramic to fill these porosities, because when we do that sintering of the different particles, a lot of times we won't do it at a temperature high enough because we want to maintain the quality of our ceramic. We'll essentially compromise and have say a density of 98%. Well, if you have a face that is melting at your sintering temperature, it will fill those gaps, and then you can reach a density of essentially 100%. Questions? All right. The metal matrix composite. This is a category of material that I was mentioning yesterday. I think we could use more. And we had a discussion about that regarding, because it can be about the same density as a piece of steel, but it's a lot more wear resistant. It actually has good corrosion resistance. It is more expensive, although it's not super expensive if we're talking about tungsten carbide, cemented tungsten carbide. So we'll just go through some of the details, how you can design for this application here. So in directional drilling, this whole shaft is rotating. A lot of times the rotation is coming from the rig above ground, essentially. So the whole string, if you say 5 miles into a well, the whole string will be rotating and wearing against the well bore. So we're looking here at the drill bit, and what I want to focus on for this example is these drive pads. What these do as the whole assembly is rotating, it's pushing against the well bore to orient. So you can essentially say, if I'm right here, the whole thing is rotating. And at the very end, when the pad is on this side, I want the pad to push against the formation, and that would be driving the bit this way eventually. So there's a special pulsation kit that is essentially adjusted to your rotation frequency. So each time the pad comes on this side, it gets pushed out, and it's wearing against the formation. You have the blow-up image of one of those pads. It's essentially a stainless steel base. It has here a composite that is 50% by volume of tungsten carbide, so a ceramic, with an alloy, a relatively wear-resistant alloy that also has precipitates in it. And inside of it, the little black buttons are cemented tungsten carbide. So it's now 90% tungsten carbide with 10% cobalt to put it together. It's a lot of work to make that one pad. How long do you think it lasts during drilling? Steve? Any other number? All right, it's few hours because I sort of, you know, I sort of lean towards. So it can be as low as 50. We try to get at least 100 because otherwise it's the reason, it becomes the reason why you have to pull the whole string back 5 miles to change those pads. And you really want to avoid that. If you have to change them each time you take the drill string out, that's fine. But you don't want to be pulling them out because now you can't steer into the well. So there's a good enough and not good enough type of design here. What happens is it's very dependent on the environment. Certain environments will essentially almost erode away the 50% layer to the point where the insert, the tungsten carbide insert, will just pop out. When you have more of an erosion situation. When you have a hard surface, then you can use the tungsten carbide to protect. So that becomes essentially, and it's not rare to have to design for these different conditions. It's easier to design to wear against something hard in this situation, and when you have something more soft that gives an erosion type of contact. A soft contact will essentially wear out more the support for these buttons. I was very surprised to see how cheap the little buttons were when we were designing this tungsten carbide. Even if it's cemented with cobalt, it was cents for the little pieces produced in large quantity. Now, as far as putting it together for this particular pad, the process for the 50% ceramic, 50% metal was a thermal spray. It was essentially a wire that was arc melted and projected on the surface, and then you have to machine to get everything flattened out. We looked into a lot of other ways to do this. The trouble is the cost of each experiment. If you're talking about wear, you can think about it, you can model it. We had some FEA work going on, but there's so many parameters that it's the test that actually tells you, oh, in these conditions it's good, in these conditions it's not good. And then the question becomes, do you want a different type of pad for different types of formation, or you just want to live with one specific design that's going to be used all the way across? So again, I think it's a good example of wear because you have the hard abrasion that you fight here with the cemented tungsten carbide that only have 10% metal to hold the ceramic together. But if it's soft, the erosion destroys the whole idea. It becomes a lot more difficult to resist a slurry than a hard contact on a hard contact. And sandstone was one of those materials that you will think it's not that hard to drill because it's soft, but it's wearing out these components. And it was also difficult to run laboratory experiment because you were wearing more deformation than you were wearing your part. So in terms of setting up, a lot of these wear experiment for abrasion is just a pin disc. So say I have a disc here of my sandstone, and I come down with my little test piece. It's anything I want. I'll wear a track into the sandstone before I actually wear out the metal. What happens in reality, as you keep going down, you're exposed to a different formation. So the tool is there all the time, but the formation changes all as well. So it's tricky, but as far as material selection, it's an example of the use of the cemented tungsten carbide, and I do want to talk about them a little bit more. The tungsten carbide here are the particles. You can have them kind of a very granular shape, and here you can see you got some big ones, some small ones. There's some idea where doing it this way, you have the small one fitting into the big ones, and you can sometimes reach a higher particulate density than if everything is the same size but crushed like these one are here. The binder you see better in this phase here. One of the idea about it, it's typically cobalt base, and we had a discussion yesterday with Matt about the corrosion resistant of that cobalt binder. Essentially, you can put about 1.5 to 2% nickel to make it resistant to seawater, where it essentially doesn't corrode. It's forming more or less of a passive layer, although here, when we're talking about a wear application, any layer you form of the surface will tend to disappear relatively quickly. So what you try to do is have a low reaction rate altogether. And that's something that is possible by adding a little bit of alloying to your cobalt binder, and that doesn't have a detrimental effect on the other properties. One advantage of these cobalt alloys is the hardening effect. You try to make sure that when you come with an abrasion particle or even an erosion, any particle contacting this microstructure, you want to consolidate the material so it doesn't form chips, it doesn't spread and remove material easily. And that's related to strain hardening. A material that has high strain hardening, typically, if you deform it, say I just do a groove. So I start with a flat surface, and then I come and I plow through. So I'm going to form a ridge here. I'm going to have the hole where my particle is, and then I have another ridge on the other side. So this is for an experiment where I'm essentially displacing a bead in this direction. The amount of pileup we call here, so this material, say we're even looking at it very specifically at the height of it, is very much related to the strain hardening. When you have these composites, one advantage is if you start deforming, you can start having the particle that contact each other, the hard tungsten carbide, and that is increasing your strength, your compressive strength. It's not linear. The more you deform, the stronger you are. And that contributes to the wear resistance. In addition to having the hard particle, in some situation, you can have no wear. But for applications of abrasion that we were talking about, you will have some hard particles in the sandstone. You'll have in any media some particle that will form essentially scratch type damage, a permanent deformation of the surface. So you have to design for losing thickness over time. And the way to reduce the loss of thickness is to minimize the amount of material that is extruding out of the surface, because in subsequent wear processes, when you have another abrasion particle that comes here, eventually you will remove the material. So in this type of ductile wear, where you have permanent deformation, your design becomes more oriented towards strain hardening, but also fracture toughness. Because when you make this deformation, you end up with a lot of residual stresses. And that's what this image shows here, where you form these cracks that are running across the scratch here. So a scratch was running this way, and you have these hairline cracks forming in other direction. Eventually you can have particles falling apart in a brittle manner. This is really a research experiment. When you look at a piece that came back from a drilling site, it's very complicated to determine what happens, because all these processes, the scratching, the removal of material from the pileup, and the brittle removal from forming cracks are all blended together. And it's hard to attribute a certain proportion to one process as opposed to the other. So I think this is a neat way, and you can start seeing here, even on the edges, you see that pileup that I was talking about. It's not really regular. This will be very easy to remove in a subsequent step, or even by erosion now at this point, because it's protruding from the surface. So all these materials, you can tailor your fraction of particle, the size, depending on what you're really looking for. Are you hoping to not lose weight during the wear? Or there are situations where you know that no matter how hard you try, you will be sometime forming these scratches, and you'll have material removal. It's something to think about. I'm showing here the fracture toughness of essentially a tungsten carbide with cobalt. So this, it does go above 15. So if we wanted to have fewer issues with wear in general, we would try to use more of this cemented tungsten carbide. But there is a cost, because it has the corrosion resistant, it has a decent toughness, it has excellent wear resistance, about the same density. But there's a cost associated to it, and in the end, if you can use it as an insert, and that's what they do even for drill bits. In general, not the whole drill bit will be the cemented tungsten carbide, but you'll have the specific part that is going to be cutting that will be. So you see the effect of grain size and the binder content. So you reach a point, and 10% cobalt is not uncommon for a cemented tungsten carbide. It gives you a fracture toughness either below or above 15, depending on your grain size and grain size distribution as well. So it's really something to keep in mind when you're trying to put together an assembly. If you're going to have parts that are going to be contacting each other, we haven't talked a whole lot about wear, but one issue, for example, with aluminum is relatively soft. And if you have an environment that is just even wet, like airframes, for example, if you have a little movement between the two pieces of aluminum, you break down your protective oxide. So we talked about aluminum having a protective oxide, pure aluminum being a great alloy for corrosion resistance. But if you keep breaking it down, now you start corroding, and we call that fretting. If we think about stainless steel, in a lot of environments, as long as you don't have too much chloride, it's a great material. But if you put stainless steel against stainless steel in an assembly, in general, you're looking for trouble if you have movement between them. So we call it galling, because the two pieces are not really oxidized. So it's not aluminum on aluminum is not going to stick because you have that oxide between them. But stainless steel and stainless steel, you have more sticking between the two components that are of similar chemistry, and they don't have a thick protective layer. So what happens is you adhere on one side, and then you can break the material at another location. So that way galling works. Say I have two surfaces, and then they're not perfectly flat. So there's always going to be one area that's preferentially contacting. And then if you happen to bind here and break at another location, now you have two surfaces. This surface is not flat anymore. So you're roughening the surfaces, and you have accelerated wear. So it's a situation you want to really avoid, and I've seen it a lot of times. Especially for piping application, where say you have a stainless steel pipe, and then you have clamps that are used to secure a cap or anything, a valve application. If these similar materials will just wear out very quickly. In a few hundred cycles, you can have very deep scar marks that are visible to the eye, and you have a high erosion rate. If you were hoping for these surfaces to form a seal, which I've seen, it's not going to happen. Eventually, you'll lose the seal, and you'll have a leak. Now, titanium is another great material. I think from a lay person perspective, it's actually overrated. I've seen the people that are in the titanium industry. They don't complain about it, but they always think about it when apparently if you go to Museum of Science, it was the case at some point that you could have different types of membership, and you had a platinum membership, but the titanium membership was the highest, the best one. It's really not the case, but it's something to keep in mind. That, if you're doing a design out of titanium, it's about 5 to 10 times more expensive than steel of aluminum, when you take into account manufacturing, because you have the raw material, and then you have the fact that it's not used as much, and it's harder to machine, for example, if that's what you're going to be doing. So it just gives you a bulk part. You're looking at spending more money. One of the reasons you would do it is the good mechanical and corrosion performance. For mechanical, essentially you have about half the density of steel, and you can get strength and fracture toughness that are not that different. So that's very attractive. You can have very good fatigue properties. For corrosion resistance in marine environment, for special pumps, it's more resistant than a lot of other materials. It depends on the chemistry. So for some industrial applications, the titanium would be resisting more the environment than than a lot of other metals. You should know about these transformations. So if we have a pure titanium a bar and that we're cooling it down, I showed you a phase diagram before, but we're just looking at the pure alloy here. We'll go from hexagonal compact to the BCC, so body centered cubic. So it's a similar transformation than what happens with steel. Steel goes from a face-centered cubic, so a compact structure, to the same BCC structure at about the same temperature. What it means, though, is when you go through that transformation, you become more at risk for a brittle transition temperature. So we know steel has these issues at very low temperature of becoming brittle. We have the same risk with titanium. If it's in that phase, if it transforms into the beta phase. So depending on alloying, you can end up with a microstructure that's either the high temperature microstructure phase or the low temperature one. And you'll be essentially just adding different alloying elements. So the alpha, the high temperature phase, because it's hexagonal compact, it's not going to have any brittle transition temperature, so that's an advantage. It's also going to be more creep resistant. So it has advantages if we're looking, say, at a turbine blade for a compressor. On the compressor side, so before the combustion in the turbine engine, that's where the temperature is low enough that you can use these alloys because of their excellent fatigue resistance, fracture toughness, and low weight, essentially. The beta alloys, you just use different alloying elements. So we have vanadium, niobium, molybdenum. These are better for strain hardening, forging, and precipitation hardening. So for kind of you can use titanium for a combination of wear and corrosion resistance in a pump, for example. So in that case, you'd definitely be looking at a beta alloy. Now, the most common titanium alloy is actually a combination of the two, so it's a dual phase structure. The titanium 6-4, it's got both vanadium and aluminum in it. It's promoting both phases. And I have an example that I mentioned about the very first class, but I want to go through it in more details now that we pretty much have more knowledge. It's essentially the component that's keeping this whole leading edge in shape. It's holding the skin, so it's an interior structure. It's also connecting to the hydraulic system for opening and closing the flaps. Here, the leading edge, essentially, for takeoff and landing. So you have it here in green, painted, and it's the same component that it has the holes in it here. As you can see, it has a lot of fasteners going through it from the aluminum skin to the titanium. It's not really the situation that you want to have. This is a lot of work to do, install all those fasteners, but it's this idea of redundancy. So if you have one crack forming, it doesn't have a continuous path like it would have if you are trying to weld or braze or join the two components continuously together. So the idea of using titanium here, I mentioned in the first class, was to be able to resist the heat from the de-icing system. So the big hole here allows for recirculating air from the combustion of the engine to go through the wing if you're taking off or landing in an icy condition, so close to freezing. So the idea of this design is to be able to resist the loads. When you pull it out, you essentially flexing the whole rib assembly, and you're pulling it back. It also needs to resist impact if you have a collision. You have to resist the marine environment, but as far as optimization, it becomes a question of cost and weight. When you've satisfied all those criteria, you can resist the load, you can resist the environment. The question now is, how much is it going to cost and how much it's going to weigh? Because there's a relationship for the whole aircraft. The way it works out is, if you want to buy one, I'll tell you, okay, I'll sell you for this weight, you pay me this much for an aircraft. And then I have essentially a weight budget. And I remember when I worked at Bombardier, there was a whole department that was essentially an accounting system for figuring out weight of each sub-assembly everywhere, so they can keep track and adjust as they went. So if they ended up designing the landing gear, oh, we're 10 pounds overweight here, now something else had to be designed lighter. They do that. They used to do that for cars as well. There was some regulatory limits, how much the car can weigh and produce so much emission. So there always be a step function where if you can make it below a certain amount, it's more attractive to the customer than the next step up. So it affects the day-to-day life of material selection. So for those ribs, for example, if it turned out that we're lighter than we expected to be, we could, make some forging. We can't use aluminum. We could use steel, but it would be a big weight penalty. But if it turns out we had that benefit working for us, you could use steel for those, because you realize you can't use aluminum and you don't want to spend money. But in this particular case, what I was looking at is essentially the choice between using different titanium alloys, but also using a wrought product that was a thick plate machined down to form the rib, as opposed to using more of a casting process, investment casting, where you form the part out of wax, you make ceramic mold with it, and then you almost cast it to shape. So we could cast this component with all the ribs, the holes, and only need to machine this exterior surface. There's a very precise tolerance that had to be met on the exterior profile, and we couldn't get it even out of the best investment casting process. So let's try to do the optimization, because we mentioned, it's a cost as opposed to weight criteria. The way we were looking at it, and this is not the exact work product, I had to redo it after I worked there, so you don't have to worry about confidentiality and stuff. Essentially, if you look from this stiffening rib to the next one, what you have is a three-sided supported plate or sheet. And that's what I've been looking at. And same for this one. This rib is supported here on this vertical edge and on top here, and it has one free edge where it can buckle. So the limiting design was this free edge buckling. So it has these very specific equation. You almost need the spreadsheet to calculate for everything, and you only have so much material that's loaded in this mode. So if we look back here, what happens when you're loaded is this whole portion here is loaded in compression. This is loaded in compression. This is loaded in compression, and then you have tension on the upper edge, at least during the takeoff and landing cycles. So you have to design. You're only going to use one material, and if you use a lightweight material, you won't have to worry too much about buckling resistance because it's going to be thick. At the same time, in the tension area, you need to use something thicker because it's not as strong. So essentially, and we know that for aluminum, for example. So aluminum, if we need a lot of it, we make it big and it's buckling resistant. It's a great material to have. If we work in tension, steel is a lot better because we can get a lot more strain out of it. So it's really becoming a compromise here. And the way of ponderating it was essentially assign a certain proportion to the tension part and the compression part. So if we go back to this, that's our compression buckling with the free edge. And we just have a full set of equation for how to calculate it. I estimated that the part in tension and compression were approximately equal. It's not exact, but it's a starting point. And then the cost of material and processing, you have definitely more money spent in processing, even with titanium, than you have for the raw material itself. So these are the different candidates that we were looking at. The aspect of processing is not included here. It's just something that was additional when I worked there, and I just didn't really reproduce it. But it's interesting to see when you take into account both the tension and the compression. It had to be a high resistance alloy, but you can see here. Essentially, thank you. A steel is not that difference. We have a 15% difference between a very expensive, less steel alloy as opposed to the titanium. So your whole design could be changed if you happen to want to spend more or less money on something. So I went over by a few minutes, I'm sorry, and thank you for your attention.